Thanks, Holly, for the introduction. Welcome to the webinar. For those of you who do not know, my name is Ming Yan. I'm principal consultant. Have been with NEO since 1998. Before that, I worked at the Heritage Water University and University of Manchester for about 7 years. And currently, I look after our produced water and oiling water measurement activities. So really the purpose of today's webinar is to give you an introduction on oilfield produced water and oiling water measurement. So there are two parts. Basically, the first part is all about general introduction to oilfield produced water. We'll cover what produced water is and oiling produced water discharge limit, and then a couple of slides discussing management options and a couple of slides discussing produced water treatment technology. And second part, I will cover basically the definition of oiling water and why we measure it, what are the measurement methods. Then I'll touch on an important concept that is measurement uncertainty, and I'll find a couple of slides discussing some of our recent work and future work planned. So first of all, oilfield produced water. What is it? What it is? And effectively, it is a waste. It's a byproduct associated with oil and gas production. It includes formation water. This is water sitting with oil with millions of years and co-produced. Condensation water. This is the water vapor condensed during the production process. Return injection water. We know reservoir when we start production, reservoir pressure is high, and operator has been using seawater or other waters to boost the reservoir pressure, and some of this water can end up with oil being produced. And also we know crude oil often contain quite a lot of salt, and operators been using fresh water to dissort the crude oil, and this water can be ended up with part of produced water. Now, typically, production process and wellfield coming and going through the first stage, second stage separator, depending on pressure. We may see even third stage of separator. Gas separated from the separator, so will go flare, or some quite often it's also cleaned and compressed and exported. And the crude oil coming from the separator will go for export, but sometime before go export, you have the dissolter there. This fresh water added to reduce the salt content. The water collected from the separators will go through a produced water treatment process, and typically in the North Sea, certainly started with the hydrocyclones, and then goes through a degasser. And these days, before overboard discharge, quite often compact flotation units is added. Now, if the produced water is going to be reinjected, either for pressure maintenance or for disposal, quite often, or particularly produced water injection, for pressure maintenance, then a filter is added to remove the solids. We know produced water contains all sorts of things, certainly salt, and some of the produced water can contain total dissolved solids above 200 milligram per liter, compared to seawater of 35 solid milligram per liter. Dissolved gas, we're talking about CO2 to H2S, solids, sand, CO2, and corrosion scale products, and like calcium carbonate and iron oxide, heavy metals and cadmium and mercury, that sort of things. BTEX, that's a single ring aromatics, that's benzene, toluene, ether, benzene, xylene. NPD, we are talking about two-ring aromatics and so on, naphthalene, phenazine, dibenzothiophene. Organic acids, we're looking at essentially carboxylic acids and naphthenic acid. PAH is a polycyclic aromatic hydrocarbon that the aromatics contain 3 or more rings. Phenols, radioactive materials, and of course, dispersed hydrocarbons. Now, what we do with the produced water, quite often in the offshore situation, it's inject or discharge. The onshore situation, it's also kind of injected and a small amount may be reused. And here is a chart from OGP international organization, International Association of Oil and Gas Producers, and the data covers 2016-2020. We're looking at the percentage of produced water being reinjected. IOGP members produce roughly about 40-45% of the total wood oil. So the data shown here should be quite representative. We can see here onshore, roughly about 80% of this produced water is reinjected, and offshore, we're looking at roughly about just over 30% of this produced water is reinjected, rest being discharged. You can see offshore, we have been witnessing small increase over the years, and overall offshore, onshore, we're looking at roughly 55%, certainly in 2020. In the North Sea, this is the diagram drawn by myself. It covers data from 2001 to 2018. 2018, this is the sort of the latest official data from OSPA. Top line, blue line, shows the number of installations handling produced water. Bottom red line shows the number of installations that practice produced water injections. Green line shows percentage of the platforms that practice produced water injections, and the purple line shows the percentage of amount of water being injected. What you can see here is between 2001 to 2018, we have been seeing a steady increase in the percentage of produced water being injected in the North Sea. So how about the amounts of oil in your discharge produced water? And here's again a chart from IOGP, cover the same period, 2016 to 2020. And so this is the onshore situations and the oil content in your discharge water. We're looking at certainly 2020, it's roughly about 7 milligram per liter. Prior to that, we're looking at 5 milligram per liter. What you can see there is perhaps the small increase in generally over the last few years. And offshore, again, we're looking at roughly about just under 20 milligram per liter oil in produced water, discharge water. Again, what you can see is between 2016 and 2020, maybe you can see a small increase, and that really kind of shows the challenges faced by treating produced water for discharging. So that's kind of all I want to say in relation to the general introduction to the produced water. The next few slides, I'm going to cover the legislation side in relation to discharge of oil produced water. Now, first of all, offshore. In offshore situation, international law recognizes 5 categories of wastewater, body water. Contaminated seawater, this is seawater used for operations such as tank cleaning. Machinery-based drainage, this is the water collected from your engine room pumping areas. Offshore processing drainage, this is the water collected from a deck. Produced water we already covered. Displacement water, now this is seawater used to compensate the decreasing level of oil in your FPSO, that's floating production storage offloading vessels, and to maintain the stability and the integrity of the vessels. And now, in regulatory requirement can be looked at different levels. Can be looked at the global, regional, and the national, and industrial body and individual operators. Okay, now the top 3, the ones I said, usually they are legally binding. That means that you have to meet the target, and if you don't, you could be really in trouble. But the bottom 2, and this is more related to best practice, and so obviously you aim to achieve, but if you don't, then certainly it's not the end of the world, if you like. And now at the global level, perhaps the best known is this MARPOL 73/78. So it came into force in 73, amended in 78. and this is by the international monitoring organizations. The wastewater covers, we're looking at contaminated seawater and machinery-based drainage. So if you want to discharge those, then the oiling wastewater content must meet the 15 milligram per liter. This is truly the global, what we're looking at, over 150 nations have signed up to. At regional, there are many of these conventions, certainly well known as OSPAR, Baltic Sea Conventions covering Baltic Seas, the Kuwait Convention covering Red Seas, and Barcelona Convention covering the Mediterranean Sea. The OSPAR areas, the oiling water discharge limits, we're looking at monthly 30 milligram per liter. And in Kuwait, for the Kuwait Convention in Barcelona, I mentioned we're looking at monthly average 40 milligram per liter, maximum daily 100 milligram per liter. For the Baltic Seas, it's aimed for 15 milligram, but if you cannot meet that, 40 milligram, aim for, if 40 milligram cannot be, and if you cannot achieve the 15 milligram, 40 milligram is still okay. And the wastewater, we're looking at offshore processing, drainage, and produced water and displacement. So at the national level, and just an example, that's Canada. And in Canada, if you want to discharge produced water, the monthly average is 30 milligram per liter, and daily maximum is 44 milligram per liter. And in Canada, oiling water can be either measured by infrared methods or gravimetric methods included in the standard method 5520. Now, at industrial association level, here's just one example by the Oil and Gas UK, formerly called the UK Offshore Operator Associations. In 1998, they set a target to, they set a commitment to achieve 30 milligram per liter. And I can tell the UK North Sea these days, average is 15 milligram per liter. And oiling produced water discharged to sea. At operators level, and here's an example from Shell. They established in 2007 the global environment standard. And in the standard, they specified if the installation is outside 5 kilometers away from shoreline, then the monthly average not exceeding 30 milligram per liter. If it's within the 5 kilometer, then the discharge limit is 15 milligram per liter. And I know operators like Total, they have a similar kind of standard set within the corporations. So that's offshore. What about onshore? What I can say is onshore, there is no global legislative framework and very few regional regulations. And in certainly EU, hydrocarbons have been classified as list 1 substance under the Dangerous Substance Directive. This directive was later incorporated into the Water Framework Directive, which is quite complex. I'm not going to go into detail, but certainly within the EU, it's in relation to produced water onshore productions, it's reinjection, produced water reinjection is considered as a kind of most cost-effective and economic options. And as far as I know, if you really want to discharge in EU, we're looking at oil water content of 5 milligram per liter. If you are really interested in onshore produced water discharge, then I would refer you to this document published by World Bank guidelines. And it was first published in 2007. And in the guidelines on the hydrocarbon side, it specified 10 milligram per liter limit. But it's not just the hydrocarbons. For onshore, we're also looking at things like a BOD, biological oxygen demand, and COD, chemical oxygen demand, as well as things like heavy metals and total suspension, sorry, the fin nose. So really for onshore discharge, there's not just the hydrocarbons, there are lots of other things. And I should point out that in 2017, the World Bank trying to revise the document, but as far as I know, it was still in the draft format. Okay, so that's all I want to talk about in terms of the regulatory requirements focusing on the discharge, oil produced water discharge limit. The next couple of slides, I'm going to touch on the produced water management options. So we know produced water is going to be produced. We also know we are seeing increasing amounts of produced water is actually produced around the world. And so what are the management options? Now, to understand management option, let's look at a schematic courtesy to share. Just imagine red is oil and gas and blue represents water. Obviously, from operator's point of view, you want to just have the oil and the gas, not the water. So the question is really you should ask is, can you do something at the reservoir level to stop water getting into the bottom hole, the downhole, the bottom hole? And if you cannot do that, can you do something at the downhole level? For example, using downhole separation produced water injections. And then if you cannot do that, then the question is, certainly for offshores, can you do something at seabed? Things like subsea separation produced water injection. Obviously, if you cannot do all of those, then the water has to come to the surface, and then we'll be looking at water separation produced water treatment. And after treatment, we're looking at reuse, discharge, or reinjection for pressure maintenance, or reinjection for disposal. So once you get through, gone through this, then the produced water management options become obvious. Really, first of all, we're looking at preventing and reducing, preventing and reducing the amount of water being brought to the surface. So we're looking at water shutoff technology, the reservoir level, downhole level, and there are some mechanical, chemical ways to do that. And then if you cannot do that, the downhole separation produced water reinjections, that becomes an option. Or for offshore situations, subsea separation produced water injections. If you cannot do those, then the water has to come to the surface. Then you're looking at treatment for discharge, treatment for injection, and treatment for reuse. So really, treatment, if the water comes to the surface, and treatment becomes critically important. And so what are the treatment technologies? And really broadly, there are two sort of main categories. One is to remove the oil, for removal of the oil and solids, and to a great extent as well. And the other one is to remove the salts. Now, for reinjection and discharging, oil content removal is very, very important. But if you are thinking of reuse, then not only oil content, salt content need to be removed, also salt content need to be removed. So for oil solid involved, we're looking at the mechanical methods, physical, chemical, oxidation, biological, mechanical, and we can use simple gravity or enhanced gravity like hydrocyclone centrifugal system, gas flotations, or barrier-based like a filtration membrane, or combination. Physical, chemical, we are looking at extraction, absorption, adsorptions, deoiler, oxidation, looking at ozone and catalytic oxidations, biologicals, and lead beds and biomass. And so for salt removal, mainly we're looking at membrane-based reverse osmosis and electrodiolysis. And we are also increasing, say, evaporation-based as well. That's heat-based. Now, for mechanical method, I thought this table is actually quite useful. And the table shows the smallest droplet, oil droplet that can be removed by the individual technologies. And so for API gravity separator, that's the simplest sort of gravity-based device. The smaller the droplets that can be removed is 150 microns. Coagulated plates interceptor 40 microns, and hydrocyclone, that's the backbone, certainly in the North Sea for produced water treatment, we're looking at 10 to 15 microns. Centrifugal systems and 2 microns, and membranes, certainly they can remove droplets at sub-micron levels. So as I said, all these technology, they're very good to remove dispersed oil, but if you want to remove the salt content, then sorry, before, when you, the mechanical methods, they are very good at remove dispersed oils, but if you want to remove dissolved compound, dissolved oil, then you would be looking at physical chemical methods such as adsorption, extraction chemicals. The difference between adsorption and absorption is that for adsorptions, the material used can be regenerated, while absorptions, once material is used, you have discarded. So for adsorption, we're looking at various things like zeolites and granular activated carbons, MPPE, and also those are the examples. And absorptions, and I got a few examples listed there as well. Extractions and CETOL, essentially it's utilizing condensates and injecting the produced water, and the condensate will extract the oil content. Chemical deoiler, just an example there. And so those are the methods for removing dissolved compound, dissolved oils. Challenges in terms of produced water treatment today, and certainly, first of all, is we are seeing increasingly more stringent regulations around the world. Certainly in the North Sea, we've seen the reduction of the monthly average of oil in water from 40 to 30 in 2007. And then in 2012, a risk-based approach was introduced. In other words, not just the dispersed oil you need to look after, but also some of the dissolved as well as heavy metals, and you need to look after them. And also in places like Brazil, previously can exclude polar component in oil and water measurement, measured oil and water, and that's organic acids. But now they have to include the organic acid in their measurement, while the discharge limit hasn't changed. So that means that meeting the discharge limit becomes more challenging. Onshore, we mentioned not just oil and water, but also COD, BODs, etc. At the same time, we are seeing an increasing water production. So on average, worldwide, we are looking at 1 portion of oil produced 4 portions of water. In places like United States, we're looking at 1 portion of oil, 7 portions of water. And in Oman, this is even worse, 1 portion of oil, 10 portions of water. And so, and also increasingly, we are trying to produce heavy oils as well as trying to squeeze the last drop of oil from existing reservoirs using chemical EOR and also ASP, that's organic surfactant polymers. And with this sort of chemical EORs, and the return produced water become much more difficult to treat than the conventional, the normal ones. So there are limitations in terms of treatment technologies. And certainly the vendor can do something here to help develop new technologies. Okay, so that's all I want to talk about in terms of the general introduction to the produced water site. So the next part is all about oil and water measurement. And the first thing first is the definition of oil and water. So what is oil and water? In general terms, oil and water, we talk about the dissolved and dispersed and free oil. Dissolved oils, that's oil dissolved in your water, you cannot really see, and that includes hydrocarbons like the BTEX and NPDs and polyaromatic hydrocarbons. And also the non-hydrocarbons, that's effectively the organic acids and phenols. Dispersed oil, these are effectively the small oil droplets. And to me, I think we're looking at submicrons to hundreds of microns. And free oil, this is the oil sitting on the water. And for this group of people, I think for produced water, really we're interested in is really the dissolved and dispersed. And free oil is less of interest to us. Perhaps a better way to show is using schematics, and thanks to friend John Washington who put together this schematics. So if you look at things like separator, you will see the gas sitting on the top, and then you below that you will see the oil. That's effectively the bulk oil or free oil, and below that we're looking at the produced water. Okay, so the red oranges represent dispersed oil, the small droplets, and then what you cannot see is the dissolved, and that's the BTEX and some BTEX and NPTs and pH. And then you've got the organic acid. Now, the organic acid, it's what is dissolved, how much is dissolved, how much is dispersed, depends on the pH of produced water. If the pH is low, then there will be more chances that the organic acid will be present in the water in the molecular form, and that's more likely it will end up in the dispersed phase. And high pH, if it's a high pH, then it's the organic acid that's going to be more present, more in terms of the dissociated. So in other words, more in the dissolved. So chemically, when we say oil in water, and we're looking at dissolved that include aromatics and BTEX, NPT, and pH, and acids, and that's fatty acids, and that's effectively the carboxylic acid, and then naphthenic acid, and then phenols. Now, dispersed oil, we're looking at the same aromatic and acids, but the bulk of the dispersed oil, we're looking at aliphatics, straight chains and branched chains, aliphatic hydrocarbons. So that's the kind of chemical side. Now, legally, oil in water can be actually quite differently defined. And OSPAR, we have this term called the dispersed oil, and this is the oil measured that need to be compared to 30 milligram per liter monthly average. And dispersed oil means the hydrocarbons in the OSPAR regions as determined according to the OSPAR gas chromatograph frame ionization detection reference method. And so what it really included means is that dispersed oil means the sum of concentration of compounds extractable within painting, not adsorbed on the fluorosil, and which may be chromatographed with retention times between those of N-heptane and 2N-tetrocotain, excluding concentration of aromatic hydrogen, taurine, isabenzene, and xylene. What it really means, that in OSPAR, dispersed oil means it's just the hydrocarbons, and the hydrocarbons between C7 to C40, excluding those taurine, isabenzene, and xylene. So all the organic acids, they are not included, and all those hydrocarbons above C40 or below C7, they are not included. And perhaps it's better to look at schematically, and this is the gas chromatograms. And so what you see is dispersed oil in the North Sea. It's really, we're looking at the area between C7 to C40, below all the peaks, if you like. But the text is excluded. So that's taurine, isabenzene, and xylene, that's excluded. So I'll repeat again, in the North Sea, dispersed oil, we're looking at hydrocarbons, only hydrocarbons, and hydrocarbons between C7 to C40, with the text excluded. Okay, so that's the definition in the North Sea. In the United States, oil in water is also called N-hexane extraction material, HEM, or total oil grease, and as determined by the method of EPA method 1664. So in the method, effectively you bring the sample into the lab, you acidify it, and then you extract with N-hexanes 3 times. And if you take the hexane extract, and directly for evaporations, after evaporation of the hexanes, what's remain is called hexane extraction material, or total organic grease. Now, if you take the hexane extraction and let it pass through silica gel, and then take the decanted hexanes, and after evaporations, what you get is a silica gel treated hexane extraction material. And here, the silica gel treated hexane extraction material is essentially all those non-polar hydrocarbons. We're talking about straight chains, blunt chains, hydrocarbons. So this part, SGT, HEM, effectively is total hydrocarbons. While hexane extraction material, TOG, it would include both, the total hydrocarbons and also those polar component that's taken out by the silica gel adsorptions. Now, the difference between HEM and SGT HEM in the United States is called water-soluble organics. Okay, so again, I think it's better perhaps shown schematically about the difference between HEM, SGT, HEM, and water-soluble organics. And thanks to John Walsh again, and he put together the diagram here. So effectively, you see here is total organic grease or hexane extraction material. It contains two parts, and first part is the water-soluble organics, and the second part is the silica gel treated hexane extraction material. As I say, silica gel treated hexane extraction material, that's the total hydrocarbons, okay, the branched and straight chain aliphatics, and this part is in the dispersed oil, and they are non-polar. Okay, the water-soluble organics, however, will contain two parts, two portions. The dark blue will be dispersed, and the light blue will be dissolved. And the water-soluble organics, we are looking at the organic acids and phenols, right? Now, the portion of dark blue, that's dispersed portions, the percentage of that will depend on the pH. As I explained earlier, if you have a lower pH, then most of the, there'll be more organic acids present in that molecular form, and that means that they're likely to be in the dispersed oil. So in other words, lower pH, you're going to see bigger portion of the darker blue there, and high pH, you're going to see a small portion of the darker blue. So why do we actually measure oil in water? There are three reasons. One for process monitoring and control purpose, and the other one is for regulatory compliance monitoring purpose, and also in terms of developing future sounding policies and sound legislation regulations. You need to collect oil in water data. So for those reasons, we need to measure oil in water. Now, what are the measurement methods? And measurement methods, there are two main categories. One is reference method, one is field measurement method. Reference method, they are mainly included the infrared-based and the gas chromatograph flame ionization detection-based or gravimetric-based. And field measurement method, we're looking at benchtop, lab version, and online monitors. Now, reference methods, they are very, very important in terms of defining what oil in water is, and also it's very important for compliance monitoring purpose. But reference methods, they are not always user-friendly, and they can be expensive. They can be also time-consuming. For example, for gravimetric methods, it involves accurate balance for offshore FPSOs and platforms. Because of movement, you certainly cannot use accurate balance over there. And also gravimetric methods, it can take 2-3 hours to get the results. GCFID for oil in water measurement in the North Sea, we're easily looking at cost, buying an instrument cost about 30,000–35,000 pounds, British pounds. So for a variety of reasons, we need field measurement method. Talking about the field measurement method, and we are looking at benchtop. And again, there are quite few benchtop methods listed here, but I'm not going to go through in detail. And if you want to know the details, I will refer you to a book chapter which I wrote back in 2011. And towards the end of my talk, I will tell you the reference. And again, for fields online measurement methods, there are 5, 6 commonly known methodologies or techniques, and and that includes laser-induced fluorescence, light scatterings, and ultrasonics and microscopy, image, and UV fluorescence. And again, I'm not going to go through the details. You can refer to my book chapter. One thing I need to emphasize is that when we talk about oiling water, it is a method. It is a method. Oiling water is a method-defined parameter. I cannot emphasize this point enough. So when you talk about oiling water, you need to refer to a specific method. If you don't, then the results can be misleading. You can easily compare apple to pears. Okay, so the next few slides, I'm going to touch on an important concept, that is the measurement uncertainty. I think it's relevant to us, certainly in terms of compliance monitoring and also in terms of accepting alternative methods for discharge reporting. Now, what is measurement uncertainty? When we do a measurement, any measurement, temperature, pressure, length, oiling water, you get a value. But is that value a true value? And I highly doubt it. So to quantify, if you like, your doubts, and this uncertainty is introduced. So uncertainty is effectively an interval, either side of the measurement, within which you can expect the true value, to lie within a given confidence. So uncertainty, we're talking about an interval, okay, either sides of your measurement value. Now, uncertainty can be large and small, and that all depends on how confident you want to be that the true value will lie within it. So the more confident you want to be, the larger the uncertainty. So generally speaking, there are 2 terms. One is called standard uncertainty, which is 68% confidence. The other one is expanded uncertainty, 95% confidence. The two are very much linked. If you know the standard uncertainty, and then multiply by this coverage factor K, which is 1.96, then you can work out the expanded uncertainty. Vice versa, if you know the expanded uncertainty, you can work out the standard uncertainty. Now, if you do a measurement many times and infinity times, then you'll get population like this. And assume it's normal, the distribution is normal, or Garcia distribution, then the standard uncertainty is actually equal to the standard deviation. And so if we know the standard deviation, then by multiply the key factor, you will get expanded uncertainty. So when we're talking about measurement, to truly define the measurement, really we're looking at, we need three items. One is the measurement value, one is the uncertainty, one is the confidence error. And here is an example, talking about flow measurement, measured flow of 3.5 liter per second is an uncertainty of 0.2 liter per second at 95% confidence. So what it really means, it means that for the measured value of 3.9, the true value can be anything between 3.3 to 3.7. So, okay, so one of the things that we often confuse ourselves is this error with the term uncertainty. Now, we know uncertainty is the interval outside of the measurement value. Error is actually the difference between true value and measured value. So in other words, in order to calculate error, you have to know the true value. If you do not know the true value, then you are not able to calculate the error. And for oiling water measurement, the true value, we can there are two ways to define true values. And one is lab prepared standards. So in other words, prepared standards with known amount of oil injected into water, and that can be defined as true value. The other one is that you use the value measured by the reference method. And so those are the two ways that you can define true value of falling water. So where do the uncertainties come from when we talk about falling water? And really, there's two aspects. One is to do with sampling. The other one is the uncertainty resulted from your analytical methods. Now, if you know the uncertainty associated with the measurement methods and uncertainty associated with the sampling, and you can use these equations to calculate the overall measurement uncertainty. And I should emphasize here is that this is the equation here. It's the standard uncertainty. It's not expansion uncertainty. Okay, so it's the standard uncertainty. Now, for measurement methods, all the reference methods when they were established, the measurement uncertainties to a great extent is known. And that's through the repeatability and the reproducibility information. While sampling and uncertainty is usually unknown, but we can make guess. Guess. We know in general sampling can contribute more uncertainty than the uncertainty caused by the reference method, measurement method. So let's look at an example in oiling water and just imagine we take samples and bring to the lab and measured by the OSPAR GCFID measurement method, and the measured value is 15 milligram per liter. And we further make assumptions that the repeatability of the measurement method is plus minus 15, and that's the 68% confidence. We also make assumption that the sampling the uncertainty would contribute towards 60% of total variance. And on that basis, the NEO has done some calculations, and we estimate the total uncertainty associated with the measured results is plus minus 7.1, which roughly is about close to 50%. So what does it really mean? For measured 15 milligram per liter oiling water by taking samples measured by the OSPAR GCFID method, we estimated that the uncertainty will be plus minus 7.1. So what does that mean? It means that the true value could be anything between 7.9 to 22.1. So the takeaway message here, when you talk about uncertainty, is that current practice using sampling and the reference method, the uncertainty can be fairly substantial. So just 3 slides and talking about some of our recent work and also plan the future work. And now we know online oiling water analyzers, they can bring many benefits. Operationally, we know it provide continuous oiling water information, can detect upsets, and also can reduce the number of samples for lab analysis. So that's from an operational point of view. And from health, safety, and environment point of view, we know that the use of online analyzer potentially reduce the usage of solvents associated with the lab methods. And also we know that online analyzers would probably give you more accurate discharge information. And also we know in the Norwegian sector, in recent years, we've seen the use of online analyzers for produced water discharge reporting. So we were asking ourselves, and how could we make the use of online analyzer become a common practice? In other words, more online analyzers can be used for discharge reporting. So in 2019, we initiated a joint industrial project called Making Online Oiling Water Analyzers for Discharge Reporting. And we had a scope work covering various aspects, including the status and using online analyzers for discharge reporting, and understanding the uncertainty associated with the current practice, that's sampling and analysis by reference methods, as I've been just discussing. And also we wanted to sort of refine the acceptance and validation criteria in relation to use of online analyzers for discharge reporting. There's already, certain OSPA in the UK, and there's already existing sort of acceptance criteria. We think that there is some scope to refine that. And a couple of other items, like one of them is in relation to the development of guidance for use of online analyzer for unmanned and subsea applications. Currently, there's nothing on that. And we want to propose some change to the existing guidance, the OSPA, the UK, and the Norwegian oil and gas. And we did the GIP, and we completed the project in October 2000 last year. And the project was sponsored by 6 operators of the one government body, and that's the UK government. The key outcomes from the GIPs, and we found that there are larger uncertainty associated with oil and water, as we've been discussing. And we felt the use of a 95% prediction tool is more scientifically sound for correlation validation checkings compared to using 95% confidence tool. And we developed some guidance for accepting use of online analyzers for unmanned installations. And we also made proposal change to the OSPA base and NOSC oil and gas ONG guidelines. And following the completion of the work, and the UK government, UK regulators made an input paper to the OSPA Offshore Industrial Committee meeting back in March, and OSPA subsequently decided to set up a work group and to further review our work and to discuss and agree change to the existing OSPA guidelines. And we had the first meeting in August, and I was there to provide the background and also propose the changes, and also mentioned our forthcoming GIP. And the OSPA work group was very supportive, and they agreed that they should wait until we will have completed the forthcoming GIP before making change to the OSPA, potential changes to the OSPA guidelines. So that brings to the new GIP, which we've just launched. And I should say, just notice the date they has run, and that was June 2021. The new GIP is entitled "The Field Trials of Online Oil and Water Analyzer for Discharge Reporting." So effectively, what we're going to do is we're looking at effectively we're going to try what we found from the last GIP, and so we're going to look at the feasibilities and practicalities of newly proposed the methodology in accepting the use of online analyzers for discharge reporting. We also are going to develop a way of calculating real-time uncertainties associated with storing order data from online analyzers. And we will propose changes to the existing guidelines, and we also look at alternative methods in terms of accepting the use of online analyzers for discharge reporting. And I hope you'll be interested in this of GIPs. And so a quick summary on the webinar. And we know produced water is waste, and we know its volume is increasing. And we also know regulatory requirements are tightening, and not just the dispersed oil, but also for dissolved oils and other potentially harmful components as well. And when we come to produced water amendment, we're looking at firstly preventing and reducing the amount of water being produced. We cannot do that. Then we're looking at treatment, discharge, injection, or reuse. And there are many treatment technologies, and two main categories: one for remove oil and solids, and the other one to remove salt. And yeah, oil and water measurement is very important, but there's a method-defined parameter. Reference methods are very important in terms of defining what oil and water is, and also for compliance monitoring. Field measurement methods are required for a variety of reasons. And I should say that oil and water measurement results, they have fairly large uncertainties, and NGL has conducted recently joined the industrial project in relation to the use of online analyzers for oil and produced water discharge reporting. And we have just initiated the new TIP, and we're going to focus the new TIP on field trials of online analyzers. Just two more slides. And useful reference, I mentioned about my book chapter, and that was done in 2011, called Oil and Produced Water Measurement, and it's freely available, and you can look at it. It will give you plenty of information about the measurement methods. And the next two documents, they are all from OSPAR, and they are both related to the treatment technologies. And the last document is related to sampling and oil and water measurements from the UK government. Also, very quickly remind that NEO's 19th produced water enabling series is coming up next month, and hope you guys can come to attend. And also, we are doing plenty of lunch and learns, and if you're interested in getting in touch with our events team. So that brings to the QA, and I'm happy to answer some of your questions.
Ming. Yeah, we seem to have lost Holly. We've had a few technical issues, so
okay.
I can do the Q&A with you, no problem. We've been having some interesting questions come through, so I will just read you the first one here. So it says, how are the organic acids excluded in the OIW measurement under the OSPAR?
Okay, that's relatively straightforward. In OSPAR, you take samples, bring to the lab. What you then do is extract within heptan, and after the extraction, you take the extract and let pass through fluorosil, which is silica, which is similar to the silica gel in the United States EPA method. So once you pass through the extract, the silica gel, the fluorosil, and the fluorosil will take off the organic acid. So, and then you take the extract for GCFID measurement, and what's measured would exclude the organic acid. Okay, hope I answered that question.
Lovely. Yeah, thank you. Okay, let's go to the next one. And what is the difference between confidence interval and prediction interval?
Okay, so yes, okay, so when you do measurement, okay, and if you get the 95% confidence interval, and that is associated with your mean value, okay, so if you got the 95% confidence interval, if you are going to predict, say, the for next measurement, what will be the uncertainty associated? What will be the next average, if you like, and then the 95% confidence interval will give you that. Now, if you are looking at predicting the individual value, okay, if you are looking at predicting the next individual value, then you need to use a prediction tool. So, in a sense, 95% confidence interval, it is associated with predicting future average, while the 95% prediction interval is associated with predicting the future individual value. Okay.
Okay, lovely. Okay, I'm just checking on time. I think we'll go to one more question. And so it says, what would it take to make the use of online OIW analyzers for oil in produced water discharge reporting a more common practice?
Okay, that's very good questions. It's a bit tricky. I think there are a few things. First of all, we need to acknowledge the use of online analyzers, And for both manned and unmanned, for manned, it means that using online analyzers, and we're going to be needing less number of samples taking for lab analysis. And now, and also online analyzers can be used for operation, benefit. But for unmanned installations, probably we have no choice but to use online analyzers. If you are going to discharge more than 2 tons of oil in produced water from the unmanned installations, and the regulation here in the North Sea is that you have to have a means to take samples twice a day, if you like, and measure the oil content. Obviously, with unmanned installations, you cannot do that. So the use of online analyzer is the only way, in my view, to do that. And so that's the first point, is the acknowledgement. Secondly, I think we, as group of different stakeholders, we all need to work together and to come up with some best practices. And certainly at the moment, the use of online analyzer for unmanned installation, there is no guidance. So, our previous GIPs and finished last year was an attempt to come up with some best practice guidance and on how to accept the use of online analyzers for discharge reporting. And so that's second aspect. I think also the vendors can do something, and the vendors can develop technology to make them more reliable. And we know that these online analyzers and particularly the fouling on the optical windows of the online analyzers, and that can be an issue. So I think the vendor can come to help. And I also think that as us all, and I think we need to recognize that, remember, and all these online analyzers, they are not fit and forget instruments, and they all need regular calibrations and maintenance. So that's another aspect we need to remember. I suppose that I hope that kind of I know maybe not the sort of full answer, but at least, and that's my view, it's how we can potentially, make the use of online analyzers, being for reporting oil in produced water, are more as kind of a common practice. I hope that answers the question.
No, lovely. That's very thorough. Thank you. I'm really conscious of time. We've got lots and lots of questions coming in, lots of really great questions. I'm sorry that we couldn't get round to them all today, but rest assured we will be in contact with you after the event, and we will get back to you and answer your questions. So thank you so much for joining us today. Thank you to Ming for presenting such a fantastic presentation and webinar to us today. As we mentioned earlier, there will be a copy of the recording and the slide deck will be available to you. We will be in touch with you to let you know how you can access that. Our next available webinar is calibrating and operating Coriolis meters at service conditions, and that will be on the 17th of November. We will get that up on the website as soon as possible, and we'll be sending out information to you about that. So please let us know if there's any other webinar subjects that you'd like us to cover. We love to hear what you're interested in, and obviously feel free to get in touch with us and ask us any questions. So again, thank you for joining. On behalf of myself, Holly and Ming, thanks for joining us, and have a great rest of the day. Thank you.
Thank you.
Thanks, Ming. Bye, everybody.
Bye.